start the recording here. Okay, and what we're going to title this is binomial probability. And this only works with those types of problems that have only two possibilities, like making or missing. If you have a problem like the one with the socks where you have red, green, blue, this doesn't work. It only works with two things, thus the name binomial. So the two things in this problem are making and missing, or hit and miss, or whatever the two things are, but they have to be opposites. Binomial probability. And the scenario, we have 4 free throw shots. Which means n is 4. In the formula that we're going to kind of stumble into is the number of trials. So Antonio had 4 shots, which in probability is 4 trials, how many times we repeat the experiment. And just to start us for this one day, I want to draw the connection to the tree diagram. So if you wanted to draw a diagram of Antonio shooting 4 times, it would be a very large tree diagram. We're going to attempt to sketch it here. Let's do it like maybe here. The first choice is making and missing, but just because this is going to get a little bit out of control, I'm going to say making is going to be letter A, and missing would be the opposite, would be not A, just to kind of simplify all this writing that I'm going to have to do. Okay, so this is the first shot. The second shot is the same choice. Make or miss. So that's second. Okay, third choice. Make, miss. And the fourth, so as you can see, if doing a diagram like this for a problem, it is a little bit too much. You could do it for something that has 4 levels, but you probably don't want to. And that was the 4th shot. Okay, and by the way, the probability of making, Antonio's been shooting 70%, and that's what I'm calling A. Probability missing then 30%. They have to add up to 100%, of course, so this is what I'm calling not A. Seven, 0.3, and beyond a couple of these, I'm not going to keep going because they can't even fit them in there. But they don't change. That's also important to these types of problems. Antonio's free throw remains the same throughout the entire season, so the percentages can't change as you go. Okay, now there's a couple of these scenarios we just talked about. A couple of these branches result in getting 1 point and tying the game. And it's probably easiest to go from the bottom here. That would be, this bottom one would be, or almost the bottom would be a miss, 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 make. So this pathway here represents making 1 point, and it's the last shot. Now there's a lot going on here, so just to try to make this stand out a little better, all of the A's, I'm going to highlight those just because, so it's visually a little easier to kind of look at quickly. Okay, the next one where you could score 1 point would be miss, miss, make, miss. That'd be this one. Miss, miss, make, miss. And that corresponds to this particular branch ending right there. Otherwise, you could do a miss, let's see, you could do a miss, make, miss, miss. That's this one. And then the last one is where he makes the first one, but miss, miss, miss. Okay, those are them. Those are the 4. All right, I'm going to introduce a new variable, or a new notation here. This is variable x, and in probability it's kind of given to be a capital X. It's a random variable. Which just means that it's dependent on probabilities as opposed to regular variables being just sort of independent. And we are going to assign this x is going to represent the number of shots made. And why this is necessary is because we can ask questions really concisely, such as, this. Yeah, not. Yeah. Okay, could you read that symbol that I just put down? That is the notation here, the math notation. It's an entire English sentence. How would you say that one? Jacob, what do you think? You turn that symbol into English and make it a question. Or not yet? Probability of making 1 shot. Exactly right. That's that entire, everything that Antonio said is what that symbol represents. It says probability of making exactly 1 shot. Okay, so that's what that symbol represents and why it's kind of useful to have this variable x in the mix. Now, there's 4 ways to do this. And we've been talking about what we multiply to get each one individually, but then we add them together to get the answer to the question. And it happens to be that they're all 0.3 times 0.3 times 0.3 times 0.7. That's, if you put the numbers in here, 0.3, there's 3 of those, and there's one 0.7. They're out of order or in different order, but they each have 3 of the 0.3s and 1 of the 0.7 in them. And there's a total of 4 branches that all have the same probability. So each one of these branches is equally likely, and the probability of any one branch is 0.3 times 0.3 times 0.3, What's kind of a quick way to write that? Yeah, to the third power. You can put a 3 up there. And then times 0.7 to the first. And I'm going to put the 1 there because you're meant to see how the formula comes to be. Okay, which if we crunch that number here, it's 0.075. Don't care so much about the number, but we want to talk about, well, how do we get this 4 without having to write out the combination, without having to write it all out? How do we get the 4 quickly? And it's something we've done in the past, kind of a while ago now. But this, by the way, represents the number of branches. That's where the 4 comes from, each with an individual probability of these decimals being multiplied. And on your calculator, if you wanted to get this, it would be 4, because that's how many trials Antonio had. He had 4 shots, and we're going to choose one of them to be the special shot that goes in. So that is 4 choose 1, which is written 2 different ways, sometimes like that with the C, and sometimes like this as a parenthesis. It's not a fraction, but it can kind of look like that. And if you put the 4 in, see if I can get it on the screen here. Not really well. And then there was a way we talked about probably in November-ish on probability. There's this NCR. And so if we calculate 4 choose 1 here, it will tell us how many branches that are, if you do 4 trials, how many have one special happening. Okay, so that's how you get the calculator to do that. You can also look at the triangle. So this is Pascal's triangle. It's how the numbers come to be on Pascal's triangle. And so let's do one more, and I think then you'll be ready to write a formula out of this. Okay, the second one we'll do is making exactly 2 shots for the win. And do you know how many branches there are that result in 2 shots? Why not? Let's for this one time, let's list out what could happen. You could make, miss, miss. You could make, miss, miss. You could make, miss, make. And I think that's it for the combos that result in the first one going in. I'm trying to be kind of systematic about this. Miss, make, miss. Miss, make, miss, make. And miss, make. Okay, so those are all of them. I think I got them all. Can you think of one that I missed? Okay, so there will be 6 branches if we found them all in our diagram. And so if we want to calculate this, the number of branches is 6. That's how many combos there are of 2 misses and 2 makes, which, by the way, is about 26%. Okay, and the way we get the 6 without having to list everything. This would be 4 trials and we're going to choose 2 of them to be special. Or for choose 2 like this. Okay, now I did a couple of examples. And I want to see if you can figure out what the formula, generally speaking, would look like. And that's the one we're going to use. Anybody think they could come up with a formula for this now that you see both of these? Yeah, we need, yeah, so it's going to start here, probability x equals, and then I didn't pick this letter and couldn't tell you where it comes from. X equals R, so that's the special, how many special they'd go in or hit their target or whatever the question's about. Okay, and we can see here there's a miss and a hit probability. There's a number of branches, which there's a way to figure that out. And then there's some exponents. And in our problem, we had 4 trials, but that, of course, could change. So n represents the number of trials that we're doing. And R is how many you get to choose that you're kind of looking for to be the special ones. This is n trials, and then R special. Okay, let's talk about the exponents that are on these. If you look at the 2 examples here, the exponent that was on the special making it in always matched the bottom number here. So this is a 1, this is a 1, and then this was a 2, and I know they're both 2s, but that's why this is a 2. And so whatever R is going to be the exponent on the one you want. In this case, I'm assuming is the good one. And then we need something to say what's left over. And before I get there here, let me throw out one with some actual numbers here so you can see. If I change the game to 15 trials, say we gave Antonio 15, he could shoot 15 times. And Antonio, how many do you want to go in? 9. Okay, he wants 9 of the 15 to make it in the basket. The 9 is how many correspond to making it in. And then what's on the 3, or 0.3? What's the exponent right here? Is 6. And Jacob, how did we get 6 specifically?
N minus R, 15 minus 9.
Yeah, you did 15. It's the leftover to make up to 15. So I'm not going to put 6. I'm going to put the way we get 6, because that's going to help us talk about the exponent. So that's the R number is 9, and then right here is going to be the N minus the R number. That's the formula. So this is N minus R on the first part of that. Okay, and that's it. That's the formula. And then since I know it's been a while since you did this on a calculator, let's also write down here how you get this symbol again. I always forget, you're supposed to put your number, your N number first, and then you go get the symbol, which is under math, probability, PRB, and then it's the NCR option. Which one? The N number. So when you put it in here, I tend to always forget this. You put 4 in ahead of time. Yeah, and then go math, over to probability, and then choose the NCR option, and then whatever you wanted to put there. Okay.